Hello, everybody. So, I've had a long and interesting day full of calculations related to the Earth's average temperature and criticizing still the statistic of 15 degrees Celsius put out by NASA. And I've come to some interesting conclusions. I've been using the energy balance equations that NASA use to calculate Earth's average temperature via calculating the differences between the ingoing radiation and the outgoing radiation. So, I mean, there's numbers of reasons to criticize these equations in climate modeling. But one of the major reasons, of course, is that they don't fully account for cloud coverage and they treat the Earth's albedo as a constant. But more importantly, I think it's because they haven't been appraising Earth's temperature at night and the changes in temperature at night. So I'm just going to go through the equations put out on this plus.maths.org website by Cambridge University, which are talking about the the um, the energy balance models used to derive Earth's average temperature. So this uses the Stefan Boltzmann constant and a measure of Earth's emissivity, which is emissivity being 0.0605, and in the numerator we have 1 minus Earth's albedo, which they give as 0.31, multiplied by 342 watt minutes to the minus 2. Then that's divided by the Stefan Boltzmann constant multiplied by Earth's emissivity. And then the whole thing is raised to the power of a quarter, which gives the result in Kelvin. And the result in Kelvin that they've come up with on this Cambridge website is 288 Kelvin. I would take issue with that since I put the whole equation into Wolfram alpha, and it came out as 505 Kelvin. Now, 505 Kelvin is really quite a lot of Kelvin. It is 231.85 degrees Celsius. Now, that's very hot indeed. Of course, that's not the Earth's average daytime temperature. It'll be hot, very, very hostile for life on Earth, I grant you, if that were Earth's average temperature. Very few organisms indeed, except perhaps extremophilic forms of bacteria and so on, could survive in those sorts of temperatures. But we've got to imagine that this is without taking the Earth's rotation into consideration. So this is what another one of the limitations of using these equations, of course, since they don't account for the rotation of the Earth. So it's only treating the Earth as receiving a certain amount of radiation per minute, and this is not accounting for the fact that the Earth spins and receives different amounts of radiation different times of day, and this is only sort of the amount of sunlight reaching the Earth at its maximum, I think, probably. And yes, so 231 degrees Celsius, that's very, very hot indeed. That's the amount of radiation, that's the temperature of the Earth if it were to be tidally locked. So if it didn't rotate at all, it's just facing the sun, it probably would reach temperatures of about 231 degrees Celsius. But then again, so I looked at that, and then I took another average for the nighttime temperature using only the amount of radiation that the Earth receives at night, which I think the only significant source of radiation for the Earth at night is energy reflected from the moon. So that's very low indeed. That's 0.0006 watt minutes to the minus 2. So that comes out in the same equation at 32 degrees Kelvin. Um, 32 degrees Kelvin being minus 241 degrees Celsius. So again, if the Earth were tidally locked, you can sort of imagine that this would be the temperature of the Earth in that situation. We find comparable temperatures in places of the moon which are constantly blocked from sunlight, such as in craters on the moon and like its poles and so on. Very dark, very cold places on the moon, which do get quite close to absolute zero indeed, yes. And but then so we can then take the average of these two temperatures. We can take the average of 505 degrees Kelvin and 32 degrees Kelvin, and then we get, what did I say it was? I think it was 263 Kelvin. I'm just going to average it again, just to be on the safe side. So 505, 32, 268.5 Kelvin to 269 if we're being technical about it. And 269 Kelvin is minus 4.15 degrees. So that is quite cold. Well, it's cold. It's not very cold, actually. Minus 4.15 degrees isn't that cold at all. And I think this is getting closer to what the Earth's average temperature really is. Since I did, yet again, some more back of the envelope calculations the other day, I took 6 latitudes on the planet. I took the North Pole and the South Pole. Then I took London, Lisbon, Congo, and Cape Town. And I took the averages of those places during the daytime and the nighttime, and the average daytime temperatures came out at about 9 degrees Celsius, so plus 9 degrees Celsius, and the nighttime temperatures came out at minus 7 degrees Celsius. So you can start to see already how using these equations you can build up some kind of coherent picture of what the Earth's average temperature is, because the average of plus 9 and minus 7 degrees Celsius, that's 1 degree Celsius. So the Earth really, its average temperature is about 1 degrees. But that does get quite close to minus 4.15 degrees Celsius, which is the average temperature for Earth using the energy balance equations. So yeah, I think I've gotten at least closer to the right answer than NASA have, since as I've said many times before, the temperature of plus 15 degrees Celsius that they put out on their websites, that's 2 degrees hotter than the Sahara Desert. So it's not going to be that now, is it? It couldn't be that. The Sahara Desert's average daytime temperature is 30 degrees Celsius. Its average nighttime temperature is minus 4 degrees Celsius. The average of those two temperatures is 13 degrees Celsius, positive 13. So really, I think we need to start appreciating more that there's huge frozen wastes on Earth. All the deserts of Earth go to sub-zero temperatures at night. So really at nighttime it gets quite cold indeed. I think minus 7 degrees for an average nighttime temperature is really kind of on the ball with that. I think it's quite a good measure probably of how cold a great deal of Earth does get at night. And I think, yeah, minus 4.15 from the energy balance equations, yeah, it does get in that ballpark. Likewise, plus 9 degrees Celsius, that I think does account for the average temperature in daytime, since again a lot of the Earth doesn't actually become positive really during the daytime in terms of temperature. Most of Antarctica doesn't, the Arctic doesn't. In the summer, like the average temperature of the Arctic in the summer is 0 degrees Celsius, so that's not very hot at all, really. But this is all very important stuff, of course, because if we don't know really what the average temperature of Earth is, how can we go about talking about changes in Earth's temperature? And how can we go about setting out averages, like 30-year averages or whatever we're doing to estimate climate anomalies? Or giving like increases in temperature of 1.3 degrees Celsius, if we're not really on the ball when it comes to how much the average is in the first place, that 30-year average from which we're taking climate anomaly measurements, then how reliable are our climate anomaly measurements in that context of getting the basics wrong, of getting the fundamentals wrong when it comes to climate science? So I hope that this research that I've undertaken today exposes some flaws with some of the details put out by very respectable bodies such as Cambridge University and NASA. I mean, this Cambridge University website, when it's talking about the energy balance equation, it gets it wrong. I fed these numbers into Wolfram Alpha and WebCalc 2.0, and they both came out with the same statistic, which isn't 288 degrees Kelvin, it's 505 Kelvin. So either someone's fudging something, i.e. lying and distorting their results, or like a campaign of mass stupidity is going on. I don't know what it is. Or like, is it like a huge desperation to constantly toe the line and present the correct results, or the result that is going to least rock the boat? And it's always in the context of climate science, because again, this that statistic comes from a webpage called Climate Modeling Made Easy. It's talking about the energy balance equations and what the Stefan Boltzmann constant is. Then you click a link on it going to the actual calculation for Earth and Moon average temperature estimates, and it comes out as 288 degrees Kelvin. But this is the point of science. This is what we must absolutely continue doing. We've got to hold strong authorities to account. We've got to hold these bodies like NASA and Cambridge University accountable if they're putting out false information. We have to check the work of other scientists. That's absolutely fundamental to science. Science without skepticism is religion and nothing more than that. We can't afford to stop questioning things and be gullible and toe the line and just do as we're told, basically, and think the thoughts that we're told to think. You know, we've got to never stop questioning, never stop holding the powerful to account, and yeah, checking people's work is fundamental to how science proceeds. And if we stop doing that, we fall down rabbit holes and blind alleys all over the place, and ultimately we fall into totalitarianism, where we're not allowed to think as we want, and we're not allowed to say the things that we want to say, and we're not allowed to tell the truth, very importantly. And was it the truth is the first victim of authority? Who said something like that? I don't remember the exact quote, but it's something along those lines. So yeah, we must never forget that, and you know, properly appraise the work of, for instance, climate scientists, but really any scientist. So yeah, thank you for watching. I hope this has been informative, instructive. I hope that you've gained something insightful from these videos. I hope that you can now go out into the world armed with just a little bit more knowledge and be a bit more questioning, possibly, and not take things at face value and not jump on the bandwagon as most people seem to, and never stop questioning authority. And yeah, thank you for watching. I hope you've enjoyed this, and I'll see you soon.